All right, good morning, everybody. I have been getting a lot of the same questions about problems like number 5, both from the 5.8 homework, and there's a couple like this on the review guide. So I just thought I'd make a quick video to go over number 5 on the homework and see if you can apply that to the questions that are similar to that on your review guide. All right, so in this problem, we're given the radioactive decay model is given by this. If the half-life of ammonia is 2.84 minutes and we have a 30 milligram sample. All right, so let's just start by substituting what we know into our equation and kind of figure out what we need to answer the rest of the questions. All right, so remember, anytime you have something sub-zero, that represents your initial amount, the amount that you start with. So it's kind of like the principle of like our interest problems. It's how much you deposited. All right, so I know that that is 30. We have a 30 milligram sample. E, remember, is not a variable. It's a number. It's about 2.7. So you'll always put the E in there. We don't know the rate. And we know that the time is 2.84 minutes. Okay, so this is not a rate. A rate will always be in the form of a percent. So if you do not see a percent in your problem, that means you do not have the rate. Okay, like in number 4, that would be our rate. In number 3, we're given the equation. So that would be the rate, about 0.87% decay. Here's our here we're not given the rate. We had to find it in that one. There's our percent, there's our rate. So a rate will always, always, always be in the form of a percent. All right, and so I am going to need to solve for the rate in order to be able to answer the questions that are covered up here. All right, so what else can we use? Because I can only have one variable per problem. I can't put n of t here, then I wouldn't have anything to solve. But I'm given that the half-life of ammonia is 2.84 minutes. So if we start with 30 milligrams of our sample, then that means that after 2.84 minutes, I'd have 15 milligrams of my sample. So my variable is in the exponent, which means we're going to need to use logs to solve because a log and an exponent undo each other. So the only thing that's being raised to this power is the e. So I need to start by dividing both sides by 30. That'll give me 1/2. And I'm actually going to rewrite this just so it looks a little bit nicer. Remember, you can multiply in any order. So I'm just going to rearrange the order of my exponent here. And so then since the base is e, I'm going to use the natural log. So then I'd have the natural log of 1/2. I can bring my exponent out front times the natural log of e, which ends up canceling. So that means that my rate is going to be the natural log of 1/2 divided by negative 2.84. So about 0.244. Okay, so let's see what the first question was now. Find a function that models the amount remaining after t minutes. And so that just means we want an unspecified amount of time. So we want t now to be our variable. So I can find it after 2 minutes or 4 minutes or 10 minutes, etc. So I'm going to go back to my original equation, plug in 30 for my initial value, and now I can put in my rate. So it's negative r, so it would be negative 0.244 times t. And this is now the general equation that I can use to find the amount of my sample after any amount of time. So this next one, it says how much of the sample would remain after 1 hour. So this one you just have to be careful because our equation is in terms of minutes. That's what the original time was given in. So we just have to say that, oh, 1 hour is 60 minutes, and I'm going to find n of 60. So I'm just going to plug 60 into my equation, 30, not pi, times e to the negative 0.244 times 60. And I get that. So that's a really small number, which, I mean, makes sense because if this is my rate as a decimal, that means that's it decays about 24.4% per minute. So you really should not have a lot of your sample left after an hour. So if that's anytime you see that E followed by a number, that means 10 to the negative fifth in this case. So I have to kind of I'm going to write this a little bit longer, 1.3154, and move my decimal over 5 times. So 1, 2, 3, 4, 5. And then I'll clean that up a little bit. So 1, 2, 3, 4. So 1, 2, 3, 4 zeros, and then 13154. And then this last one, how long will only 10 milligrams of the sample remain? Okay, so for that one, I'm going to use that equation, but now I'm looking for a time. So I want there to be 10 grams. I started with 30, negative 0.244 t. I'm solving for my variable, which is in the exponent, so I'm going to have to use logs to solve. So 10 divided by 30 would be 1/3. My exponent is by itself. I'm going to take the natural log of both sides so that those will cancel. And so my final answer would be the natural log of 1/3 divided by negative 0.244, which is how I got that 4.5. Okay. All right. So just to kind of recap again, we started by doing this because we were not given the rate. Okay. The rate will always, always, always be a percent that you'll change to a decimal. So if there's no percent in your problem, you don't have the rate. So even if you see this doubles or this triples or something like that, that's not a percentage. That is just telling you how much would be remaining after that amount of time. So that's what that half-life is here. So you'll use that doubling or tripling or whatever it is to figure out what this value would be after this amount of time from your initial value. Okay. And so I posted the rest of the work to this 5.8 homework this morning. And also we'll post the work to the review guide around 8:30. And the Zoom today will be at 1:30. And just let me know if you have any other questions.